Hello all. Good evening, everyone. Welcome to the interview preparation session for today. Hope will some participants join today also and involve in the discussion as well. Okay. So this is the questions we were discussing yesterday. Random forest or multiple decision trees. Before that also we have discussed some haphazard questions which are also related to the things of data science in the field of data science. We will also look into some questions which are also important to us while moving forward, not in the field of data science, as well as the kinds, the things, the questions which are also related to data science, right? Okay, we'll start with our next question. We have discussed about this kernel trick and confusion matrix, ROC curve, wave curve, all those kind of things. But I want some examples like what are both, like false positive and false negative are equally important or not. See, we know that true positive is required to us, false positive is also required to us, but I want to know, means I want to give you some insights to you guys that how these things are also important. Where did you going to see all those kind of answers? That's what I'm looking for, and that's what I want to tell you about, right? Okay, so I will write examples where both false positive and false negative are important equally. That's what my question is. Examples where both false positive and false negative are important equally. I will give you some examples so that you can clear your doubts, right? Okay. So while studying about data science, you might have heard about the fields of banking, and where the risk is analysis, the risk is more fraud analytics kind of things, right? Suppose a bank is going to give you loan, then he has to the bank has to choose some fields. The bank has to clarify all the things, right? In banking fields, but lending loans are main sources of income to the banks. If you are going to take some loans from the bank, then that is more important that you are whether you are going to pay back the refunding the amount or not. That's what they generally want to know. But if the repayment rate is not good, then there is a risk of huge losses instead of profits, right? If you are bank is giving you some rupees money and you are not repaying that in a proper manner, or not the bank is not taking so much of the things, means interest kind of things, then there it might happen that the bank is going to lose some, there is a risk of losing something, right? So giving out loans to customer is a gamble, as banks can't risk losing good customers, but at the same time they cannot afford to, means like acquire bad customers, like those who don't want to take the money from the bank, but they are not even taking back, right? Okay, in those cases, those fraud kind of risk kind of things, this case is in like it is a classic example importance of false positive and false negative scenarios, right? Whether you want to lose means you do not want to lose the customers which are loyal to you, but at the same time you don't want to involve the customers those who want to fraud, means those who are going to be fraud, right? Bad customers. Is that understood? Yeah, very good evening. Akhil is only there or anyone else also there? Okay, so we'll move to the next question we have today. We will discuss the questions which we have in a bit details, right? The things which you might not have thought about, right? We have heard about support vector machine, but what kernel tricks we have studied yesterday, if we want to visualize something in the 3 dimension or higher dimensions rather than 2 dimensions, then we are generally going for kernel tricks, which is also a SVM technique, right? But is it good that before SVM we will go for PCA, principal component analysis, right? That's what my question is. Is it good to do PCA? Is it good to do PCA, which is dimensional or dimension or dimensionality reduction for before? Is it good? That's what my question is. Is it good to do PC or dimensionality reduction before fitting a support vector machine? We will discuss it in detail. Yeah, Salini. Hello. That's great. That's great. Just look at the questions and listen to me carefully so that you will able to answer those all questions, right? Is it good that this technique is what I am saying is PCA or dimensionality reduction before fitting a support vector machine, right? See, uh, let's come to the point first. What we are going to do in dimensionality reduction? What we generally do is we generally taking care of those features which are mostly important for our prediction, or mm, which are mostly independent variables, but that suits to our dependent feature, right? If the features number is greater than observations, like we have so much of columns, so much of data, then we generally facing some issues while doing support vector machine kind of algorithms, right? In those cases, it is better to do dimensionality reduction before fitting a support vector machine, so that we can visualize the points clearly. Did you get my point? So that we can visualize the points clearly, right? Good. It means the answer of the question is yes. Done. So we will move to the next question we have. Uh, uh, in every problem statements, like whenever we were reading about data science, after modeling part, sorry, after EDA part or data preprocessing part, whenever we will think of any problem statement, the only thing comes into our mind is what? Linear regression. But we have some points, we have some things to keep in our mind, that how this linear regression comes into picture, and what are the what are the things which are assumptions of linear regression. Like in probability, we are doing that probability, sum of the probability is always equal to 1, and it varies from 0 to 1. Those are the assumptions. Those are not assumptions, those are the points which needs to be taken care of while doing probability, right? If something, someone says that the probability of this outcome is equal to 1 point something, then it is not good, right? Probability always comes under 0 to 1, right? So what are the assumptions while thinking about linear regression? That's what my question is. Okay, let me write. What are various what are various assumptions used in linear regression? I want some answers, as I can see that some participants are also there. Yeah, okay, just line assumption is there, linear and independent. Okay, not an issue. But what exactly I want to say is, that's great. That's great. You guys are answering and responding. Salini, I also want you to respond to the questions, right? Okay. So linear regression is done to generally best to get the best fit line, right? The sample data used for modeling represents the entire population, right? These are the assumptions. If we will take a sample and we want to make inferences from the sample, then that inference is what we are going to made is all for the total population, right? The sample data used for modeling represents entire population. Then there is the next assumption is, there exists a linear relationship between x-axis variable and the mean of y-axis variable, guys. See, whenever we are evaluating our linear regression model, we generally focused on ordinary least square method, where we find r square, adjusted r square, then we are checking for p values, right? So before going that, we need to go for y actual and y predicted. For that, we need to find the relationship between our dependent variable and independent variable. That's what most important thing is, right? Okay. So the next point will be like the residual of variance is the same for any values. This is called homoscedasticity, right? Homoscedasticity must have to be maintained. Heteroscedasticity is not allowed, right? So the variance is the same for any x value. That's That is a great point. That is what means like important is also right. The observations are independent of one another. Did you get my point, guys? The observations are independent of one another. If we will pick one observation and then we will go for another observation, that is for different. Like we will check x-axis variable once, we will check x1, x2. See those kind of variables, those kind of coefficients. Like we generally go for what beta 1, beta 2, beta 3. All those variations, all those observations must have to be independent. Then the last point is most important, guys. Y is distributed normally for any value of x. Y, which is the output variable, what we can also say that is an dependent variable, that must have to be distributed linearly. Did you get my point, guys? That must have to be distributed linearly, right? Great. So extreme violations of we have like read out those problems, the assumptions we have. If we will violate the assumptions, what will happen? If we will violate the assumptions, it it can result to redundant kind of thing. It will not show what the things are, right? Smaller violations of these results, greater variance and bias also. So if you violate the result, then it might happen that we will find variance and uh, bias and variance, right? Is that clear, guys? Good. So we will move back to our next question. I got also answers from Salini and Akhil. That's great. Okay. We have heard about the things like L1 normalization or L1 regularization, that is lasso and reads also, right? L1 and L2. I want to ask one question. How is feature selection performed using regularization methods, right? That is my question is how how is selection performed using the regularization method? That's what my question is. How is feature selection performed using regularization method? Yes, Akhil. Yeah, I'm also getting some answers. Okay, sharing. Regularization is used to control the overfitting problems, that is L1 shrinking. Okay, that's great. That's great. Okay. Okay. So we'll discuss without delaying further. We have so many questions to discuss, right? So the actually the method of regularization, in addition of penalties, is it generally gives penalties to different parameters in the machine learning models for reducing the freedom of the model to avoid overfitting issues, right? We are generally dealing with overfitting issues and underfitting issues. To dealing with overfitting issues and underfitting issues, we generally penalizing our parameters. We generally penalize the parameters in our model so that we are resolving the overfitting issues. So there are various regularization methods available in as we know that in linear regularization method, that is lasso, which is L1, and regularization etc, and the linear model regularization applies penalties over coefficients, right, that multiplies the predictors. If we will give penalties to our parameters, then only we will get good results, right? So the L1 regularization has features of shrinking coefficients to 0. Thereby it makes it can easily be removed the from the model so that our model will perform better. Yeah, L2 squared magnitude of coefficient you add, that is also great. Okay, so in mm, like for L1 regulation and L2 regulation, we generally thinking of our model, right? So before our model, what can I say? We have to give concerns about how the model is performing. If that is if we will face overfitting issue, then we will go for this regularization parameters. Yes or no? Great. So what I will do is I will go for some techniques like uh, L1 regularization is there, L2 regularization is there. Those are the methods which generally removes the overfitting technique, right? Means overfitting issues. Okay, that's great. So we have our next question. The next question will be from the probability chapter. We will go to probability now, and I will write the question and so that you can understand. How do you identify if a coin is biased? That's what my question is. How do you identify if a coin is biased? There are coins like, how do you identify that whether a coin is biased or not? Okay, to identify what we generally do. there is a method called hypothesis testing. We have better understanding of that, right? To identify this, we have to perform hypothesis test, right? What is null hypothesis then? We will have to choose some, we will have to make a sentence that is our assumption, which is the H naught parameter of our null hypothesis, right? According to the null hypothesis, the coin is unbiased. We have to choose, think of like that. We have to think of anything like whether we will think that the coin is not biased or like that, right? According to the alternative hypothesis, the coin is biased. Yes or no? If null hypothesis is saying that the coin is unbiased, then that is 50% probability chance that the coin is alternate hypothesis, which is 50% only, right? So what we will do, we will have to calculate, we will have to do some observations, some right. So what we will do is we will flip the coin 500 times. We are generally doing an observation. We are kind of doing an observation. We will flip the coin for 500 times, and we will calculate the value of p, right? Then we will compare the p value against the alpha, right? Based upon two-tailed test. That is, if the 500 times we will get, and then two-tailed test says 0.05, that is alpha value, right? 0.05 divided by 2, we will get 0.025. Then if the p value is greater than alpha, then what will happen? If the p value is greater than alpha, then null hypothesis holds good. The coin is unbiased. If the p value is less than alpha, then we can reject the null hypothesis. That's it, nothing else. Right? Great. So we will move to the next question. I also hope I got some answers from you guys, right? That's great. That's great. Okay, we have seen that in the 27th number of question, we have seen that it is good to do PCR dimensionality reduction for SBM, yes or no? But what is the importance? We are generally reducing the number of features so that it is better, it gives better visualization, right? We will discuss a bit more about dimensionality reduction. What is the importance of what is the importance of dimensionality reduction? That's what I want to know. Yeah, I'm waiting for some answers. What is the importance? To remove correlation, to get performance, useful large data sets. That's great. That's great, as Akhil. Yeah. So we'll discuss that, right? See, in the process of dimensionality reduction, the dimensionality reduction constituents reducing the numbers of features, right, in a data set to avoid overfitting or reduce the variance, right? Generally, we kind of perform those kind of things to reduce the overfitting or to reduce the variance. If there are mostly four to five advantages, but I will discuss all those kind of advantages, right? We will discuss one by one, right? So the first advantages is the reduction. This reduces the storage space and time for the model execution, right? If we will choose number of a less number of features, then it is also kind of taking care of the model. It gets executed in less time. Yes or no? Yes. So the next uh, important thing is it removes issues of multicollinearity, thereby improving the parameters of interpretation of the model, right? That is what removing the correlation, what Akhil says. That's great, right? Make it easier for visualizing the data when the dimensions are reduced. If the number of data sets, if the number of features are less, we can visualize the data properly. That's what it is saying, right? It avoids the course, avoids the course of increased dimensionality. Got it, guys? Okay. We will discuss our next question a bit longer, so be patient for that, and we will visualize how that and how is the things actually happening, right? We have seen, we have thought of, we have heard of mm, the parameters, right? Hyperparameter tuning, grid search CB is there, random search CB is there, but what are the things happening inside, right? What are the things going on whenever we are telling about those things, hyperparameter tuning, whether we are searching like grid search parameter or randomization search, what is that exactly happening, right? That's what I want to discuss, right? So how the grid search parameter and different from our grid search parameter, different from the random. Yeah, this is the question. How this grid search parameter is different from random search tuning. Okay, let's go to the Jamboard, and I will make you understand how these things are happening actually. Okay, so suppose think that this box is for grid search, and this box is for a random search, right? So we have a point here, we have a point here, we have a point here, we have a point here. I will make you understand totally, right? Say this, don't look into the diagram, and be more focused on the concept, right? So this is what I am talking about. If we have points like this, and what a random search does and what grid search does, that's what only we want to look into it, nothing else. Yes. So this is for uh, grid search. This is for random search, right? So what a grid search does is grid search generally goes into like this. This line kind of things. It will source like this. This is like a pattern, right? It will go like this. If you will look into this one, this two, this is three, 4, and 5, like that in y-axis also. But in random search, it is different. It will go for haphazard directions, right? So this is randomization. It will randomly pick up some point and go for checking and all kind of things. The hyperparameter will be tuned like that. So why is that happening? How this how this shows good result? That's what we generally want to look into, right? So tuning strategies are used to find the right set of hyperparameters. Yes or no? We generally kind of thinking of hyperparameters which will be suit to our programs or models, right? Hyperparameters are those properties that are fixed and model specific, right? It is model specific. We generally do all kind of hyperparameter tuning to define the model. Yes or no? Model specific before the model is tested or trained on the data set. So both the grid search and random search parameter means random search tuning strategies are optimization techniques to find the hyperparameters, best hyperparameter or efficient hyperparameter. Right? Did you get my point? That's what I'm saying. But in the case of grid search, this grid search, this is our random search. So this grid search, what I am saying is here every combination of a preset list or hyperparameter is tried out and evaluated. Suppose think of this point is carried out first, then it will be taken out to the problem, then will be checked, this will be checked, this will be checked. Again, it is going to be repeatedly happening, right? So the search pattern is similar to searching a grid. Grid means you know that what grid means, where the values are in a matrix and searched in performed. Search is performed. This matrix I have drawn, right? Rows and columns are there. Each parameter set is tried. Each parameter set is tried once, and their accuracy is tracked. Every time each parameter set will be tried out and will be tracked, right? After every combination is tried out, the model with the highest accuracy is chosen as the best one. We want to choose the highest accuracy, that's why we are going for best accuracy kind of things. Got it, guys? Good. So the main drawback here is that if the number of hyperparameter is increased, the technique suffers a lot. Suppose think that we have 100 hyperparameters and the optimum hyperparameter is 99. So it will take lot of time, right? So the number of evaluations can be increased exponentially with increase in the hyperparameter. This is called problem of dimensionality in a grid search. If the dimensions are more, then grid search is going to take a lot of time until it finds best accuracy hyperparameter. Got it? So if we'll jump into this random search, guys, in random search what happens, it will randomly search, right? In this technique, random combinations of hyperparameter set are tried and evaluated for finding the best solution. Some bunch of points will be taken into consideration and will be chosen. Then we will find whether these points are suitable for not, whether these hyperparameters are going to give the best fit model or not. That's we will find from that, right? For optimization, the source and the function is tested at the random configuration in this parameter space as shown in the image. I have mm, drawn that image also, right? In this method, there are increased chance, like what can I say? The finding of optimal parameters is followed from the pattern only, right? We can directly form from the pattern, or we can directly choose 5-6 points and we can directly go for that. So there are chance that the model is trained on optimized parameters without the need of aliasing. We can directly go for suppose think of in the first second attempt only we will get the bunch of parameters, those which are important for us. Yes or no? Right. So the next point will be the search works best when there is a lower number of dimensions, as it takes less time to find the right set. Right. If the data set is less, then it is better to go for random search optimization, so that we will go for good. That's great. Okay, we will move back to our next question in a bit. So we will look into some MCQs, guys, right? We will look into some multiple choice questions today. Is that fine? For all of you? Okay. So we'll discuss some MCQ questions, and I will also write what is that and how it is being done. Right. So in MCQs means I need some short answer. Right. What is masking? Where did you find this term? What is masking in outline analysis? That's what I want to listen. I want in the chat window some answers. Yeah, I got some answers also. Okay, says if a outlier is present, but we are not considered that outlier is outlier, covering a simply normal data point. That's great. That's great. What is masking? In outlier treatment, yeah, in outlier treatment, outlier exists, but we fail to detect that. Yeah, that's okay. That's okay. That's great, guys. That's great. It is simple. It is as simple as that. If an outlier finds, if an outlier we detect, but what we fail to detect that as an outlier, right? Okay. So I will give a bit tougher question right now, right? These small questions are you are already known that. Okay. In transformation, guys, we heard about some transformation techniques, right? Box-Cox transformation, square root transformation, log transformation, exponential transformation. But when the lambda value is zero, what kind of transformation is this? What kind of transformation is this? That's what I want to know. What kind of transformation is this? If the lambda value is zero, guys. Uh, I also got some answers. Akhil says this is post. Zero transformation. There is nothing like, okay. This is also called as log transformation, guys. No, no need to worry about that. We will also learn that what is all those kind of things. So this is if the lambda value is zero, then it is called as log transformation, right? That's what I want to say is. Okay. So we'll have a next question, right? Okay. As we have studied about, we are means dealing with log transformation. I have one more question about logarithmic function. What could be the range of logit function in the domain? Means logistic regression, we have a range, right? What could be the range of logit function in the domain of 0 to 1? That's what my question is. Okay. What is that? Log of odds. We are generally talking of log of odds. In our logistic regression, that is the classification statement. What will be the range of values? Is it minus infinite to infinite, or is it plus infinite, or something else? Right. When we talk the natural logs of the odds function, we get a range of values from minus infinite to infinite generally. Means if the domain is 0 to 1, then we will definitely get the range of values from minus infinite to infinite, right? That's great. Okay, hope it was good, and it went well throughout the weekend, right? So I will deal with you in the upcoming week. We will meet again with in this interview preparation session. After that, thank you all. That's it for today. Thank you. Thank you, everyone.